In this video, we're going to learn about the central limit theorem. The central limit theorem plays a very important role in what we're going to do in the next two chapters. So it's important for us to understand it and know how to use it. Consider the population of all Maryland residents. If we select a sample and find the average height of the people in that sample, that would make the sample mean, represented by x bar, the random variable. Well, we might want to know what kind of distribution does the sample mean have? Well, if we've selected a sample and if we're finding that sample's mean and that sample mean is our random variable, the central limit theorem will tell us what kind of distribution it has. Here's what the central limit theorem says. If the sample size is greater than or equal to 30, technically speaking, the sample is selected with replacement, which means you would pick a person, measure their height, send them back to the population, then pick another person, measure their height, send them back to the population, then pick the third person. Well, if you're doing this, you might end up picking the same person multiple times. If that happens, no big deal. Okay, but in order for the central limit theorem to apply, technically you're selecting your sample with replacement. And it says as long as your sample size has 30 or more, then the sample mean will have a normal distribution. Actually, it's approximately normal, but it's so close to normal we can just treat it as if it is normal. The mean of the sample average distribution will be the same as the mean of the individuals in the population. The standard deviation for the sample mean's normal distribution will be equal to the standard deviation for the individuals in the population divided by the square root of the sample size. Now, if the sample size is less than 30, the sample mean will still have a normal distribution, but only if the individuals in the population have a normal distribution. If the sample size is greater than or equal to 30, it doesn't matter how the individuals in the population are distributed, the sample mean will have the normal distribution. But when the sample size is less than 30, then you can only say that the sample mean has a normal distribution if the individuals in the population have a normal distribution. So let's say for all the people in Maryland, if we took all the individuals and got their average height, the population mean would be 64.7 inches and the standard deviation 2.5 inches. How about we find the probability that a sample of 50 people will have an average height of less than 65? Well, since our sample size has more than 30 in it, we know the sample average will have a normal distribution. So I'm going to draw the bell-shaped curve here. The mean of the sample average distribution is the same as the mean for all the individuals, which I just said was 64.7. Now in this question, we're asking about the probability that the sample average is less than 65.0. So I mark 65.0 and shade to its left. Now, in order to find out how much area we've shaded, we're going to have to convert everything into z-scores. Remember the z-score formula, value minus the mean divided by the standard deviation. Well, the value that we're converting in this case is not some individual's value x, but the sample's mean, x bar. And the mean of this distribution is the same as the mean of the individuals, represented by Greek letter mu. And the standard deviation of this distribution, if you remember from the central limit theorem, is the standard deviation for the individuals divided by the square root of the sample size. So we're going to put in our 65.0, that's the sample average that we're converting. We're going to subtract the mean, which is 64.7, and then we're going to divide that not just by 2.5, but we're dividing it by 2.5 over the square root of 50. Now, if you work out that calculation, and the best way to work out that calculation is to do the subtraction in the numerator, get that value first, then divide these two numbers in the denominator and get that result, and then divide your two results. Okay, so if you take 65 minus 64.7, that would give you 0.3. And then if you took 2.5 divided by the square root of 50, you would get whatever that number is. Take the 0.3 from the numerator, divided by whatever your result from the denominator is, and that's where you would get the 0.85. Now that 0.85 is your z-score. You're looking for the area to its left. So you would just go to the standard normal chart. Okay, we've done that a few times already, so I'm not going to keep flipping back and forth to the chart. But if you look up 0.85 in the standard normal chart, you should get 0.8023. Okay, let me go to another question now. Let's say that people's water consumption is normally distributed. The mean is 218.4 ounces per week, and the population standard deviation is 25 ounces per week. If a random person is selected, what is the probability that he or she drinks more than 224 ounces of water per week? Well, this question is about a random person. This question is about an individual. So there's no sample size or no sample mean or anything like that to talk about in part A of this question. We're talking about an individual, so you need to know how the individuals are distributed. Well, we're told that they are normally distributed. So you can go ahead, draw the normal bell curve, put the mean 218.4 in the middle, mark down your 224 and shade to the right. Okay, we're shading to the right because the question says more than 224 ounces. Now, in order to get the area that we've just shaded, we're going to convert everything into z-scores. So remember, value minus the mean divided by the standard deviation. The individual value is 224, the mean is 218.4, and we're dividing by the standard deviation of 25. Well, when you subtract the numerator, that gives you 5.6. We're dividing that by 25, and we get 0.22. So basically, if we're dealing with a standard normal distribution, we'd be looking for the area to the right of 0.22. Well, remember, when you're looking for the area to the right of a z-score, you look that z-score up in the chart, and if you do, you get this number, which is 0.5871. I don't think my scanner picked that up very well, but that's 0.5871. That would be the unshaded area to the left. If we're looking for the shaded portion to the right, remember what we have to do. We have to take that number away from 1. 1 is the total area, subtract the unshaded portion, which is 0.5871, and we're left with 0.4129 as the shaded piece here. Now, what if we select a random sample of 40 people, and we want the probability that their average water consumption is greater than 224 ounces per week? Well, here we're dealing with a sample, and we're asking about their average. So if the question is about a sample's average, you got to ask yourself, what's the sample size? In this case, it's 40. 30 or more, you can automatically say that the sample average has a normal distribution. If the sample size is less than 30, you could only say that you have a normal distribution for the sample mean if the individuals have a normal distribution, which in this case they do. So even if our sample size was something like 20 or 25, we'd be okay. But it's 40. So it really doesn't matter how the individuals are distributed here. We know that the sample mean has a normal distribution. So I'll draw that bell curve. The mean of all the individuals is the mean of this distribution. So 218.4 is in the middle again. And it's basically the same question, greater than 224. So mark 224 and shade to the right. Now the difference here is when we go to convert to a z-score, remember the standard deviation for this sample average distribution is the standard deviation of the individuals divided by the square root of the sample size. So we're going to have to factor in the sample size here. Well, anyways, we have the value 224 minus the mean 218.4 divided by the standard deviation 25 over the square root of the sample size, which is 40. So when you do 224 minus 218.4, you get 5.6. If you do the 25 over the square root of 40, you get this number, 3.9828. You might have more decimals. If you keep 4 or 5 decimal places here, your final answer should turn out accurate, which in this case, when you take the 5.6 divided by the 3.9528, you get 1.42. Okay, so remember, subtract in the numerator, get 5.6, divide the two numbers in the denominator, which gives you 3.9528, then divide those two results to get your z-score. Now 1.42, we're looking for the area to the right of that in a standard normal distribution. When you look up 1.42, the area to its left, the unshaded piece would be 0.9222. When we take that away from 1, we get the shaded piece here is 0.0778. Now notice there's a big difference in the answers. Basically 41% chance that an individual drinks more than 224 ounces of water per week, but only about a 7, almost 8% chance that a sample of 40 people would have an average water consumption of greater than 224 ounces per week. Why is there such a big difference in the results here? Well, the reason why is whenever you select a sample, in that sample, you're most likely going to have people who are above the average and people who are below the average. And those people tend to cancel each other out, so the sample average tends to be close to the population average. If you've got individuals above the population mean and individuals below the population mean, they're going to cancel each other out, and the sample average will, for the most part, stay close to the population average. We see that in the fact that the standard deviation is decreased. Remember, for the individual, the standard deviation was 25. So that would be a wide bell shape, indicating that these individuals could kind of be all over the place. But when we factor in the sample size for the sample mean, the standard deviation is 3.95, which is significantly less. That means this bell shape is much narrower, and that shows us that the sample mean will most of the time be close to the population mean. Okay, here's a picture that would compare the two distributions. Okay, the wide bell shape would be the individual's distribution. The narrow bell shape would be the sample means distribution. Okay, notice for the sample mean distribution, the big part of the curve, most of the area is right here around the population mean, indicating that most of the time you'll get a sample average close to the population average. But for individuals, that curve is kind of spread out, suggesting that you've got a decent chance of getting people who are all over the place. If you look at where 224 is, notice there would be much less area under the sample mean distribution than under the individual distribution. I want you to keep this idea in mind that the sample mean stays close to the population mean most of the time. Just file that thought away in the back of your mind, because that's going to be a very important thought for us when we get to chapter 8 and we're doing something called hypothesis testing. Okay, the central limit theorem is the foundation for that. One of the things we learn from the central limit theorem is that the sample mean will be close to the population mean most of the time. Not always, but most of the time. Keep that thought in the back of your mind as we get ready to move forward in this course.